Good morning, everyone. I'm sorry for that previous week. I have another work, so I cannot have the course. Today we will move to the chapter 4, and next week we have a final. No, not final. It's a midterm examination. So the content of the midterm examination is in previous slides, not including chapter. Okay. Because the time is limited, so I am afraid that you cannot recognize or are familiar with the material of chapter 4. So our midterm, just the text content only the previous slides, a previous chapter. OK， 就是我们考试就是考这一章之前的其他章。我大概算过，好像是4个 chapter 吧，还是5个 chapter，4个 chapter， 对不对？我们就只考4个。OK。So today we will talk about the chapter 4. It's about the charge particle equilibrium and the radiation equilibrium. So this kind of equilibrium talk about the radiation detection and the radiation dosimetry. This is very important in this chapter because we have some assumption. We have some assumption of the dosimetry calculation and the measurement. So we needed to know the difference, or we needed to know what condition we should be achieved. And then this theory can be applied into different situations. All right, so the first one is charge particle equilibrium. We call it CPE. So we will using the CPE to talk about these things. And for equilibrium, that means equal for something. Okay? And its adjective is charge particle. So that is equilibrium of a charge particle in a cavity. In a cavity. Okay, so the cavity should be a target of you are interested. Maybe your detector, maybe your DNA, or your silicon chip, anything of it. The region of you are interested, and this is a cavity. Cavity. This cavity should describe the radiation interaction produced the charge particle, and in this area, your region of interest, it's equilibrium or not. Okay, so this is the main idea. And next one, we need to talk about the RE. RE is the radiation equilibrium. That means all of the radiation equilibrium. So in this chapter, we will talk about these two main ideas. Okay, so you must get the ideas. And when we go back to the content, you can see that it talks about the radiation equilibrium first. So this radiation includes all kinds of radiation. Okay, that is non-charged particle and charged particle. For non-charged particle, it talks about photon and neutron. Okay, and the charged particle talk about electron, proton, alpha, or heavy ion. Okay, so these things you should get it together, and then we will using this idea in a situation. And this kind of situation is a kind of example. So this example using the measurement of exposure as our region of interest. So when you measure the exposure, actually you're using ionizing chamber. And for ionizing chamber, please discuss with your classmates what is ionizing chamber to measure exposure. Okay, just recall what you learned from previous and summarize what is the exposure using ionizing chamber. Give you 1 minute, please go ahead. 请跟你的同学讨论怎么样量测铺路，然后是用游离枪。那要考虑什么东西来看我们今天要讲的主题，好不好？来1分钟。继续讨论，继续讨论。好，来，一下，谁上面？2点和2 ，OK， 那边2点哪里？在哪里讲？对，哪些是它的有效范围？对啊，就是会有一个 region of interest 嘛，就是X空间嘛，至少有X空间，对。所以之前这个范围的话，是在你们想要的这个力量的话，在哪？空箱，那空箱大小会影响到你的设计。那快速讲空箱大小、空箱小的分别，或者这样子。我拿一张大的来量，再拿一张小的来量，就是这个解释。对不对？好，需不需要什么条件？好。他们自己来出去。这才是个对。好像是设计来的那个造型效应啊。 Alright, so I found all of you can discuss the correct interaction. So actually the first one you must notice some list of things. The first thing is what is the size of the chamber, right? So here is the air, and you're using radiation to interact with this air. And because it's called ionization chamber, and it also measurement of exposure. So when you see the exposure term, that means the medium must be air, and the radiation must be photon. 就是你在量测铺路这个值的时候，铺路这个值的时候，辐射一定是光子，然后呢，物质一定是空气，没有其他的。Okay? Alright, so this is the definition of exposure. Alright, so we're using this definition. So when you see this term, you should think about this one. Photon interact with air. No other choice. And actually, this photon should be smaller energy. So that should be, its energy should be smaller than 3 MeV. Actually, the correct definition of it. Okay, so go back to the charge-particle equilibrium here. So we talk about the charge-particle equilibrium here. We talk about the size of the chamber. Compare with the range of the electron. the range of the electron is charged particle, right? So for photon, it interacts with the air and it creates electron. So electron range and the chamber size. So because these two terms relationship, we can say it achieves equilibrium or not. Okay? All right. So for this one, charged particles range depend on what parameters? Energy, right? So the range of electron depends on its energy, and its kinetic energy has higher energy, and its range is longer. Okay, and could you define your chamber according to the range of the electron? Actually, sometimes you can. You just select the determine the size of chamber. Okay, but actually the size of chamber is fixed. Okay, so you must confirm in your application situation, is this energy produce the range can achieve this equilibrium or not? Okay, so this is the main idea, just a main idea. And then we move to other things. Your target can be a detector, solid detector, or DNA, or silicon chip, or anything. Okay, so this is an idea. And after you move to this one, you should think about the dose, not exposure. Okay, so because this material is not air, so we move from exposure term from here to here is dose, radiation dose. Okay, but also when you talk about radiation dose, you always can measure dose, but what is the actual dose? You must talk about equilibrium situation. Okay. All right, so sometimes CPE could be failure. Failure, that means the equilibrium situation does not exist. So we must correct it. Correct of our measurement result with the appropriate factor. 就是如果当 CPE 不存在的时候，很多时候可能是这样。那我们就不能量吗？当然不是，我们只是会用其他的方法来修正这件事情。So it's a kind of a correction. Okay? Is it clear here? Okay. So another word here is a transient. Transient means it is not exactly equal, but it has a factor. That means I always have large ratio than you 2 times. So 2 times is this kind of relationship. So although failure, that means it does not equilibrium, but it have some definite relationship, like the ratio, like in and out have a ratio, and this ratio is fixed. So we call it a transient charge particle equilibrium. Okay. All right. So here is all of the idea of this chapter. All right, so we move to radiation equilibrium first. Okay, so when we talk about radiation equilibrium, we're using RE to express it for a smaller internal volume. So here, you must define the region of you are interested in. So here, we talk about is a small volume, and this volume has a V, and following the 4 condition. So if the following condition is achieved, then the radiation equilibrium achieved. So the first one is the medium is homogeneous. So the medium here, oh, okay. So I think you should incorporate with this figure. Okay, so it mentioned about the volume here, and then it is homogeneous. And what is this kind of homogeneous? It's talking about the atomic composition. Okay, so not just the mixed, and the element is also the same or similar. Okay, so this is homogeneity. The second one is the density composition of the medium is homogeneity. So the other is density. So the first one is atomic composition. The second one is density composition. The density composition is homogeneity. And the third one is radiative source is uniform distributed. So that means the source. This is talking about the radiation source. The radiation source is uniform. So if it is a nuclear medicine, then the radioisotope is uniform distribution. Okay? And the fourth one is no electric or magnetic present. Because the field will influence the charged particle direction. Okay, so no this one present. Okay, if you check all of the medium here, so here it has two volume here, external volume. Okay, so you go back to see this figure. We have a volume, small volume here, and this is surrounding material over here. So the first one you should check the medium here and the medium here is uniform or not. Two kinds of uniform. The first one is atomic component uniform. The second one is density uniform, density composition uniform, or homogeneous. Okay, and the third one is, what is the third one?
Source is uniform.
Okay, so if we talk about radiation, so inside it, so we maybe say some radioisotope. Let me see. So here it say a homogeneous isotropic source distribution. So that means the source, radiation source, is uniform distribution. Okay, so you must check of this. And the fourth one is no electric or electric field and magnetic field. Okay, this is four condition. Okay, once one condition does not exist, you must find out how to correct it. 就是这四种条件，只要有一种不存在，你就必须要想办法去修正它。这样可以吗？ Okay, the most common situation is the composition, the density is different, such as the air is over here and the radiation isn't mean. So the density is different, right? From air to human tissue. This is a kind of density, not uniform. Oh no, not homogeneous, not uniform, not uniform. Okay, so this is a kind of things. So once you face this problem, you need to do another correction. But before you discover more complex things, you should memorize the four conditions here. Okay? Alright, so once we say these four conditions achieved, then we can do an assumption that is okay, the last one, I'm sorry, I did not mention it here. The S is S is greater than D. So what is the S? S is the minimum separation of the volume of your region of interest of radiation dose. And the second one is D, is the maximum distance of perturbation, such as charged particle range. Okay, so that means your separation should be greater than your charged particle range. So you can say write down like this one, charged particle range. Okay, and sometimes we just write down the range, electron range, because if you have other particle like proton, like alpha, which one has the longest range? Longest range, largest range. 哪一个会有最长的路径？射程 charged particle, say. So here has an electron 1 volt. Another. Okay, actually this is the maximum one. If they all have the same charge, same energy, kinetic energy. 如果它们有相同的动能的话，电子是会走最长射程的。Okay, so when you discover all of the charged particle here, you can find that you should choose the maximum one to do the judgment, right? You don't need to check all of it because the electron range is the longest one. So you choose this one to do this kind of judgment. Okay? Alright, so if your separation is greater than this one, then these four conditions make sure this exists, radiation equilibrium exists. And when this exists, then you can say that the radiation dose is the energy deposit inside your target of interest. And here is its mass. So the radiation dose is the deposit energy divided by the mass. But it's identical. It should be mentioned that all of the conditions exist. Because the energy deposit inside here could be the energy of Q. So we will mention it later. Alright, so here is the definition. So before we go to the absorbed dose, you should check the situation over here. Actually, you should answer radiation equilibrium exists or not. Alright, so the energy deposit inside here, we're using epsilon to describe it. Okay, and this epsilon could be right like this one. Okay, and this one talk about the radiation in and out. So the first one talk about the uncharged particle in and out. The second one is charged particle in and out. Okay, when we get radiation equilibrium, then in equal to out, in equal to out. So all of this equation only left this one. And we will say that the radiation equilibrium exists. Okay? But for first things is we must make sure the four condition in the previous slide. Okay? Alright. So here is our result. So what is the separation? Separation means this one, okay? And the range means this one. So your region of interest is in here, and here is your source, type of source. Yeah, okay. So here is the example. All right, before we go through to the radiation equilibrium, actually, if this exists, then this exists, okay? But if this exists, this will not definitely exist, depend on the situation. So we will check CPE first, and then we move to RPE, RE, okay? So for RE, for CP, so if RE exists, then CPE exists. If RE doesn't exist, CPE not necessary. Not you should check for CPE. Okay, so this is the situation. So we move from this way. So we check the CPE first, then we check up RE second. Okay. All right, and I give you an solve problem direction. First one, you talk about the CPE. You should check the electron range. Okay, and if you move to the RE equilibrium, it's talking about the radiation. This kind of radiation means all of the radiation, and photon and the neutron has longer interaction range. So it talks about these things. And move to the radiation, we focus on neutron and photon, or X-ray, photon. So we talk about the mean free path. Okay, so for charge equilibrium, you should check the separation is greater than this one. So greater than the range, right? S must greater than D, right? And this D is the electron range. And for the neutron and the gamma or photon here, we will talk about the separation should greater than mean free path. And what is the mean free path for photon and the gamma? Mean free path is the inverse of linear attenuation coefficient. 就是它的平均自由路径是由它的直线衰减系数的导数所做成的。那这个平均自由路径的意思就是指说，我假设光子都不作用，但是呢，它平均走到什么样的长度的时候就一定作用。那这个的话呢，其实就是把它的那个 exponential 从0积到无穷大，对不对？所以呢，它其实是这样子，它那个不作用，然后呢，这个积到无穷大之后，然后一次作用，那这个地方的这个值，这个是 exponential term， 然后这个值的话呢，就会是它的 mean free path， 然后这个是 x， 这个是它的光子数，还有 x， 这样。所以它的平均自由路径是，其实每一个光子可能这一个光子走那么短，下一个光子可能会走那么长。可是它事实上就是都是不同长度下去作用的，所以在这个 exponential term 里面的话呢，我们其实不知道实际每一个应该是说它是几率性的一个产生，而我们就要做，因为我们需要做数值的运算嘛，我们需要做一些假设，所以我们假设就会以平均值来做。那什么叫平均值呢？那就看我们想要看的重点是什么。所以呢，这里的话呢，平均自由路径就会指说，光子如果我一爬全部下去，然后它的直线衰减系数都是 μ 的状况下，这个 exponential term 是一个 exponential minus μx 的这个状况下的话，我积分的平均结果，那它平均可以走多长 ？OK， 所以平均自由路径、平均寿命都是这个意义。Okay, so we move to the radiation, the photon. we talk about the neutron and the gamma. So its mean free path is 1 over mu, 1 over linear attenuation coefficient. All right, so here is the idea. Okay, so 4 condition first, and these 4 conditions exist. Then we say we achieve the radiation equilibrium, and then we can using the term here to calculate the radiation dose because we know the deposit energy here. Okay, and then go back to judgment of the equilibrium exists or not. You should think about the S and the D relationship. And if your region of interest greater than the charge particle, then range, charge particle range, then we say it's charge particle equilibrium. If your separation greater than the mean free path of your non-charged particle, then we say it's radiation equilibrium. And once the radiation equilibrium, that means charged particle equilibrium exists also. Is that clear? Okay. All right, so we move to charged particle equilibrium here. So when we talk about the charged particle equilibrium for the volume V, so you think about the interesting is the V over here. Okay, so go back here, the V over here. So this is the volume. All right, and S means from the source. Here is the source. Source. It will emit radiation, and if it is a radioisotope, if here the source is a radioisotope, give me an example. If it will emit beta, right? If it is iodine, what kind of radiation it will emit? Beta and gamma, right? All right. So you must check about the source over here and check about its radiation. If it only charged particle, you just need to check the range. This range, if this emission happens here and the electron go this way, beta, go this way, then this is its range. Then we will check about this volume, the separation of this radioisotope and this boundary of this volume. Its separation, this is greater than it or not. Okay? 这样清楚吗? Okay, so you must check about the source. And check about the source emission, what kind of radiation. Okay? If it may be emit alpha, beta minus, beta plus, and gamma, right? Okay, so if this, you check of the charged particle equilibrium, and for this, because this exists, this also exists, right? Okay, so for this one, we check about the RE. Okay, I give you an answer. Charged particle equilibrium could be exist, but radiation equilibrium not necessary. Okay, 就是结果论哈，结果论就是 charged particle equilibrium 在这种情况下一定会产生，除非你这一个 volume 太小，不然的话它一定会发生，因为那个带电粒子的射程其实没有太长。OK， 所以这个你就有一个 idea。那如果它 emit 出 gamma 来的话呢 ？If it emits the gamma ray and this gamma ray has MeV energy, so its mean free path always greater than centimeter. So that would be exist from this volume. So the RE does not exist. So it's a kind of ratio. So here you should think about is have a transient equilibrium here. Okay? Alright, so I'm sorry I should go through here. Alright, so why would we need to check of the charge particle equilibrium? Actually, you only can if you have a chamber here. Your measurement is any kind of a charge particle deposit its energy over here. Okay, so this is the charge particle. Okay, and they deposit its energy here, so we say it's epsilon. But the real thing is that this charge particle, if from the isotope, okay, so the charge particle could be like this one, and maybe like this one, right? And you only measure the things, the charge over here and over here, okay? But the charge here and the charge here, you missed, right? So for measurement, you only can determine this volume. The charge particle deposit its energy over here. But sometimes you cannot using your chamber anywhere. You should using some theoretical to estimate the result of the dose or the result of the energy deposit inside this volume. If you cannot measure it, how can you do? What can you do? Actually, you will using calculation. Okay, so let's move to here. Okay, so you will using the calculation method to do the dose estimation. 就是有些时候你并不一定能够将你的游离场放在那里去做量测，因为游离场只适用于空气跟光子，对不对？那如果你在一个 volume 里面你是没有办法去量测的时候，那你可以怎么样推估呢？事实上你就要用理论的方法来做。所以我们要做一件事情，就是我们要去评估一个东西叫做理论跟量测之间的关系，我要确认。那我的理论计算到量测的时候，量测是真实的状况，我们是不是一致？然后我们一致之后呢，我们就会用理论推算的方式去算，比如说是 DNA 的这种剂量，或者是去算那个是 chip 的剂量。可是实际在确认之前的时候，我们是用量测的，我们是用游离场量测的这样子去做。所以你要先确定你的理论计算是否正确，用量测来评估。可是在这个过程当中，你需要知道它们的关系，什么样的状况下你的量测结果跟你的理论计算是一致的，这样可以吗？所以我们今天在做这整个讨论的时候，就是在解决这件事情。然后后面的事情就是说，如果是其他的东西的话，你全部都是用理论计算。Okay, so for the whole situation, you can not determine the DNA dose. You just can using the simulation or something to do the calculation, and then you must check your simulation or your calculation is correct. So you need using a measurement to check it, but your measurement has a finite element. So you need to know if your measurement is consistent with your serial calculation. Okay, so that is the whole idea. So you need to check of it. So here is the result. Okay, and so we go back. We would like to do some measurement, and we should check the correct things. All right, so you only measure this area. Then you must check the theoretically situation. Here and here exists. And this is not count. in your situation, but you measure the result over here. And you have count all of this range, but actually you only measure part of it. Okay? So we talk about the equilibrium is the things you did not count and you measure it equal to the things you should count, all of the things, but you missed this. Okay, so it's talking about the thing here and the thing here equilibrium. OK， 好，所以答案就是，实际上在这里发生的时候，因为你的 region 在这里，所以你在这里发生的时候呢，理论上计算它不会算到它，它不应该算到它，因为这个事件不在它的这个保尔能中发生。可是在这里发生的时候呢，你不一定量到，不全部，因为它跑出去了。所以我们需要确认一件事情，就是我不应该，我没有算到的，但是有量到的，和我应该要量到的，但是却没量到的这个部分，它们两个要一致。那这个时候我才能说我的理论跟我的实际量测是可以吻合的，这样可以吗？因为你永远要用量测去 check 事情，可是量测有限制。到这里 OK 吗？大概的 idea 是会是这样。Alright, so this is just a simple figure to express this idea. Actually, you need to more Congress define. So charged particle indirect for indirect ionizing radiation for external source, and the charged particle equilibrium will exist in the volume V if the following conditions satisfy to the volume V. So here is its result. And actually, the main thing is here. So I just mentioned that, right? So here, S should greater than D. And this D should be a mean free path over charged particle. And because the mean free path is greater than charged particle, so here say that the separation greater than mean free path, then CPE also exists. So here talk about the RE. So here is all exists. So we take 10 minutes rest and go back. All right.